All right, so this is a video on another non-equilibrium quiz. This is number 2, and it'll be similar to the first one. So let's see how it goes here. Maybe go a little quicker through the material. So the first one says Mr. Rod catches a tire if the mass of the tire is 10 kilograms. All right, so if you remember from the first one, we had an individual that was fishing, and at the end of a pier or something along those lines. Let's see. Oops. Try and draw this. Or at least sketch it. All right, we have this tire in the water, and just like last time, we're going to go ahead and free body diagram this. I think it says that the tire is 10 kilograms. And what else do we know? It tries to pull a tire out of the water vertically. What is the magnitude of the tension in the line? If the net acceleration is... Oh, okay, so the net acceleration is actually going to be downwards. So the pulling force upwards is going to be so small that the tire is going to be accelerating into the water. All right. So all right. So this is gonna okay. So let's maybe go ahead and add that right here, that the acceleration is 2 meters per second squared downwards. And we're probably going to most likely define down as negative, but we'll worry about that in a second here. All right, so forces here, we only have 2. We have the upwards force of tension, and since the tire is accelerating downwards, we have the downwards force of gravity, which will be larger, or the larger of the 2. And so we have something like that. Let's sum our forces here in the y direction. Yeah, we can probably fit it in over here. Sigma Fy equals MAY. We have tension. Let's go ahead and decide here which way is which. So we'll go ahead and say up is positive and down is negative. Even though it's accelerating downwards, and which is the negative direction, let's see what happens if we call it our standard way. So then here we know that tension is a negative force, or is a positive force, and force gravity is a negative force, and it's going to be the larger of the 2. Mass is going to be 10 kilograms, and the acceleration is pointed downwards, so we're going to have to go ahead and apply the sign here. Normally we don't apply the sign right to the variable when we don't know what it is, but since we know what it is, we're going to have to apply that negative sign to the acceleration. All right, so let's go ahead and get a little more information here. So t is what we're solving for. We don't know, so we'll just leave it like that. Fg is mg, and the other side is 10 times negative 2, which is negative 20 newtons. All right, so back over on the left, we have the mass of the tire, which is 10 kilograms, times baby g, because this is the tire's weight. And it's equal to that net force there of negative 20 newtons. So this is showing that even though tension and force gravity are going to fight it out, in the end there will be more negative force with the negative 20 newtons. All right, so we'll go ahead and do a little bit of math here. We have 98.1 newtons is equal to negative 20 newtons. And then we'll go ahead and add 98.1 to both sides. And that's going to be, what is that going to be? Positive 78.1. All right, so we see that gravity is larger at negative 98.1 newtons. The net force is negative 20 newtons. So tension is only going to supply 78.1 positive newtons, which is 20 newtons weaker than force gravity. So there we go. There's our answer there for tension. All right, let's go ahead and add a sheet of paper here, and we'll try the next one. Okay, so problem 2 here. Assuming there is no friction, find the acceleration of the two-block system. Also find the tension in the string. All right, so for number 2, we have something like this. Let's get rid of that. So once again, no friction on the table up here. Go ahead and draw it a little bit larger. Okay. All right, so we're expecting something like this. Draw a dot here. It's not really working so hot. Oh, dang. Let's just keep it black. All right, and we'll start by free body diagramming, right? Go ahead and add a little texture here to the table so it's a little easier to see. We'll start by free body diagramming. Obviously, force gravity, force normal, and tension. Over here, tension, right, pulling up. Whoops, let me switch to blue. And FG downwards, and it's going to be the larger of the two. We know there's no friction, so the top block, the 4 kilogram block contacting the table, has no frictional force. The 8 kilogram block isn't contacting the surface, so we don't have to worry about friction. Tension are a pair of Newton's third law forces, or force pair. They are equal and opposite. And we know that because the 8 kilograms is a larger mass, and there's no frictional force, that this set of masses is going to accelerate off of the table like this. And we'll call this the positive x direction. So on top of the table, right is positive x. On the side of the table, down is positive x. And yeah, and that's our coordinate system. So let's go ahead and solve the problem. We want to know what is the acceleration in the x direction. So let's go ahead and work in the x direction. All right, so sigma fx equals max. We should note here that with this block first, that Fn and Fg are not x forces, because on top of the table, positive x is right. So only T is an x force. If there was friction, then that would be a negative x force, but there's not. So we have T as a positive x force for the block on top of the table. On the side of the table, we see that T points in the negative x direction, because on the side of the table, down is positive x. So T is negative x and Fg is positive. So on the side of the table, then I have Fg as a positive force and T as a negative force. And notice that the Fg's are both Fg, and that's incorrect, right? Because this Fg is smaller, so I'll call it Fg4, and this Fg is larger, so I'll call this Fg8. All right. Let's come back down here. This is going to be Fg8. Okay. All right, then. Okay. One other thing we can fix here is that the mass is actually the mass of both blocks. So this is going to be 4 plus 8, which is 12. Now, the reason that's the case, that that's 4 plus 8, is because our system is both blocks. We said this last time, that we were going to define this yellow dotted line, that this is the system. All right, right there, the 2-block system. Okay, so if that's the case, you can make a note here if you like to. All right, both blocks. Let's go ahead and go to the next step here. We can see the T's are going to cancel. So we're going to end up with FG8, which is going to be the mass of block 8 times baby G is equal to 12 kilograms times AX. Obviously, the mass of block 8 is 8 kilograms. Baby G is 9.81. Not worrying about signs there because it was already applied as a positive sign up in the step before, right? That was positive FG8. So we don't have to apply another sign now. All right. Now let's go ahead and do a little multiplication here and see if I have my calculator. All right. 8 times 9.81 is 78.48. So AX is going to equal 78.48 newtons divided by 12 newtons, which is 6.54 meters per second squared. I think I had my units wrong, didn't I? Yeah, that should be 12 kilograms. All right, so notice the positive sign on 6.54, although sometimes we will solve that and we will only get magnitude and we'll have to apply a sign, but it is in the positive x direction because the blocks are accelerating off the table, which is in the positive x direction because we defined it that way. All right, good. Hopefully that's making sense. Let's go ahead and add another page here. Now we want to solve for the tension in the rope. And we said last time that now you have to pick one block to use as the system. I think it's easier to pick the top block because there's only one force on it. So let's go ahead and do that. And let's continue to work. Let's say the 4 kilogram block is the system. And let's continue to work in that in the x direction. So let's say the sum of the forces in the x direction is equal to MAX. The only x force on the 4 kilogram block we said was tension, and it points in the positive x direction. The mass is just the mass of the 4 kilogram block only, so this is going to be 4 kg. And and that's one of the changes of switching the system. The acceleration is the acceleration of both blocks, meaning one block alone has the same acceleration as both blocks because they're connected by that string. So it's 6.54 meters per second squared in the positive x direction. All right, so we're expecting something like this. We do the math, and it gives us 26.16 newtons is our tension. All right, what if we had picked the other block? Let's just solve it just to show you what would have happened. So 8 kilogram block is the system. Once again, you don't have to do this because you already have the answer. But if you had picked the other block, you would have did it the same way. Except now, you have two x forces. FG8 is pointed positive x, T is pointed negative x. So we're saying FG8 minus T. And then the mass would be just for the 8 kilogram block. Acceleration is still 6.54. Let me rewrite that. multiply that by 8 is 52.32 newtons. Over here we have the mass of block 8, because Fg is the same as mg, right? M8 times g. So I have mass 8 kilograms times 9.81. Sign was already applied, so we don't have to worry about that. Minus tension. All right, 8 times 9.81. Didn't we do that? I feel like I did that one already, but maybe not. Let's go ahead and multiply that. 78.48. All right, subtract that to the other side. So I'm saying we'll subtract 78.48 newtons from both sides. Notice that because the other side is going to be negative, well, both sides are going to be negative, we're actually going to get a positive answer. So we do the math there, we get a negative t equals negative 26.16 newtons. Negative signs will cancel away, and we're left with t equals 26.16 newtons. All right, so we just proved that had we have picked the 8 kilogram block, we'd still get the same answer as the 4 kilogram block. All right, and then the net acceleration of either block or both blocks together is 6.54 meters per second squared off of the table, or in the positive x direction. All right, let's go ahead and solve the last one now. Let's go and add a couple pages. All right, so in the last one, we have a 5 kilogram chicken nugget and with spicy mustard sauce. And it is on a ramp. So let's draw that ramp. And it looks like the angle is 20 degrees. Call that theta. It says that the coefficient of kinetic friction, let's draw the chicken nugget, I guess, first. Okay, and with spicy mustard sauce. All right. That doesn't really look like spicy mustard sauce, but okay. It works. And we know that mu k is equal to 0.2. And yeah, and so let's go ahead and add a little more color here. Maybe some green here for this angle, just so we know what we're talking about. First thing we want to do is what is the magnitude of the nugget's acceleration? So we want to know what is the acceleration down the ramp. So what is AX equal to? All right, so that's our question mark there. All right, so let's start with a free body diagram on the nugget. Let's go ahead and add some forces here. Obviously, force gravity, straight down. Force normal, or 90 degrees to the surface. It is moving, it is sliding down the ramp. How do we know that? I think it's a poorly written question, but we are given mu k, so we can assume it's sliding down the ramp. Yeah, but it should say it's sliding down the ramp. I think it's because I wrote the problem, and so I am changing the problem currently as we're working on this. I'll just make a little note there. That should be in there. All right, let's go ahead and add a little bit more. So we have force, friction, kinetic then pointed up the ramp. And those are our three forces that we have acting on the nugget. All right. So for next thing we got to do is pick an axis system to work in, and we're going to go ahead and tilt it. So we're saying that this is positive y. We'll call down the ramp positive x. We'll call up the ramp negative x. We'll call down and right negative y. Okay, so something like that. Let's call down the ramp positive x just because we're accelerating down the ramp. And so we'll get a positive acceleration at the end. Let's go ahead and add some components here. Call this FGX. Call this one FGY. Add our right angle in. All right, add theta, which was that green angle. And this is going to be, I don't know, 20 degrees. Okay, so we have something like this. Redraw step would just show that where we don't draw FG anymore, but we replace it with its components. The redraw step would show this. I'm going to draw FGX a little bit larger than force friction kinetic because it is accelerating down the incline. I guess I should have used dotted lines there. Whoa. Let's see if I can redo that and try and erase that a little bit better. All right, that'll work. I'm going to do a dotted line. All right, just because these are components and I don't want you to forget that. So something like this, right? All right then, let's go ahead and work in the X direction. We're probably going to have to go to the Y direction as well, but let's see if we can get it going with this direction first. So positive X forces, we said down the ramp is positive, so FGX. Negative X forces, force friction kinetic, equal to the mass of the nugget. What was it, a 10 kilogram nugget? 5 kilogram nugget, which is what is that, like 11 pounds? So still pretty heavy chicken nugget. All right, so 5 kg. Acceleration, we don't know. All right. FGX we want, but we know that we're going to need a little SOHCAHTOA to find it. If we go back up here, we can see FGX is an opposite. FG is our hip. So we're going to use sine there to solve for FGX. So go ahead and write that down. Sine theta equals op over hip. Sine 20 is equal to FGX over FG. FG is the same as MG. So let's go ahead and multiply both sides by FG. Kick that over here. Once again, FG is MG, but I'll replace that in a second just so I'm not doing too much at once. Mass was 5. And what we're going to see is that FGX is equal to, I think that's 49.05. Times the sine of 20. 16.78. All right. And there's our FGX. So let me go ahead and try and separate this. Okay, so we have over here 16.78 being subbed in for FGX. Force friction kinetic, we don't know, but we do know it's equal to mu kinetic times Fn. So that's just based on this formula right here, which I can just add off to the side. That force friction kinetic is equal to mu kinetic times Fn. All right. And so let me extend this orange line here. All right, then. Mu kinetic, what did we say that was? 0.2? I think the problem told us. So so now the problem is we have Fn hanging out here and is an unknown that we need to move forward. And we want to solve for Ax. So because we have two unknowns here, Fn and Ax, we need another equation. And so this is when we look to the y direction. So I'm going to come down here, sum the forces in the y direction. So even though we're accelerating the x direction, we are not accelerating in the y direction. This is because if we look up here, force normal and FGY will be equal and opposite. The nugget isn't speeding up into the sky or down into the plane. So we can say then Fn points up, FGY points down. Mass of the nugget is 5 kg times 0, which is just going to be 0. So we're left with Fn minus FGY is equal to 0. Fn then is equal to FGY. FGY is an adjacent, so we're going to have to do a little SOHCAHTOA here. How do I know that? Just based on this. See, FGY is an adjacent here. So, okay. So we're going to use the cosine formula. Cosine of, was it 20 degrees? Is equal to FGY times FG, or divided by FG, which is mg. Right, this is the same as mg. So we can go ahead and multiply both sides by mg. Cancel, cancel. This is over 1. And we're left with FGY is equal to mg cos 20 degrees All right, so let's go ahead and plug this in. All right, I'm getting about 46.09. All right, which is close to the hypotenuse of 49.05. We knew this was going to be the case because cosine does well with the small angles like 20 degrees. Units here are newtons. This can then get subbed back into our equation, 46.09. Multiply that by 0.2. Still got the 16.78 hanging out over here. Subtract that, set it equal to 5 kg times AX. Do a little multiplication. We're getting about 9.22. All right. 16.78 minus 9.22. What does that equal to? Is that 7.56? Yeah. All right, divide both sides by 5. Don't forget the kg. Newtons divided by kg is going to be meters per second squared, because it's a force divided by a mass is A. A equals F over m. So I'm just utilizing the idea of Newton's second law. A equals F over m, so we get meters per second squared for our units. We'll cancel here. AX is equal to 1.51. All right. And this is going to be in the positive x direction, or down the incline. Okay, so that's it. Pretty much normal inclined plane problem, except in the x direction having a number that was not 0 for our acceleration, and it was down the ramp, and calling down the ramp positive. Having to sub in for F friction kinetic as mu k Fn. Having to look in the y direction and solve because of Fn. We needed an expression for Fn, and we did that down here. Fn is Fgy, which we found, and then we did a little SOHCAHTOA to get Fgy, which is 46.09, so Fn is 46.09, so we plug that in and solve for an acceleration down the incline of 1.51 meters per second squared. And that's it. All right. Good. I think that's it. All right. Anyways, have a good day.